Let's take a look at a CSES graph problem, shortest routes 1. So what's going on here? We have a graph, and we want to find out the shortest path from some particular starting city to every other city. And importantly, the edges have a length, or actually a price. Yeah, they're a little inconsistent. So we want to find the cheapest price or the shortest length. It's all the same thing. The graph has 100,000 edges, 100,000 vertices, 200,000 edges, and the costs are up to $1 billion. So we can't use BFS for this because the edges actually have like weights or costs or prices on them. BFS only works if all the edges are the same length, or yeah. So we need to use Dijkstra's algorithm. That's sort of, this problem is basically asking you to implement Dijkstra's algorithm. So what's going on in this example? There's 3 nodes and 4 edges, and we're supposed to output the distance from city 1 to all the other cities. Well, the distance from 1 to 1 is 0. That's always going to be true. The distance from 1 to 2 is 5. This one is 6, but actually you can go from 1 to 3 and then 3 to 2, and that costs 2 plus 3, which is 5. So that's how we got that. It's better than 6. And to get from 1 to 3, well, we could follow this edge or this edge, but this one's cheaper. It costs 2, so that's what we're going to do. So that's how the example works. So let me explain how to implement Dijkstra's algorithm. Shortest routes 1. And we'll do this in C++. So Dijkstra's algorithm is actually just like BFS, except instead of using a queue, you use a priority queue. You get the cheapest thing out instead of just the next thing. Okay, so we just read in edges, which are A, B, and a cost. And we want to 0 index. Are the edges bidirectional? A one-way flip. Okay, it's important. Okay, so we're going to make an adjacency list, and first number is the vertex, and the second number is the cost. So we're going to keep track of the best distance. I always need to look up the API for priority queue. Push, top, and pop. Okay. Okay, so we're always going to start from city 0. I think that's probably what they say, right? Yeah. It's 1 indexed. Okay, so pull off the cheapest item. Actually, so a priority queue by default gives you the largest item, but we want the smallest item. So what we can do is, instead of passing in less as the comparator, we can pass in greater. And actually, we want to we want the cheapest by distance. So we actually need to have the distance in the priority queue so that I can sort by it. Not just the vertex. Right, so visit the cheapest path. So this is the key point of Dijkstra's algorithm, is that if you look at the cheapest path to a sort of undetermined vertex, that will always be the best path possible. And the reason is that all of the edges, this doesn't actually work if there are negative weight edges, because then it might be good to take a longer path initially so that you can then take a negative weight edge, get you back to being shorter. But as long as there are no negative weight edges, the shortest sort of currently unexplored path must be optimal. And the reason is that any other path that got to that same vertex would have to take one of the other, currently unexplored paths. And those are all longer. So that's already like worse, right? You're gonna have to add more edges to that. Yeah, so that's the deal. And actually, the way that we're going to implement it, you might see a vertex that you've already seen before. So that's fine. We're just going to say only if we haven't been to this vertex yet. Let's see. So for each edge out of this vertex, which has some cost or weight and also some destination, we can add that sort of potential path to the queue. And this is it, actually. So if we haven't been to this vertex before, then mark down that this is the shortest path to this vertex, and for every edge out of this vertex, that's a way to reach y. So write down that we might want to reach y that way. And if we have already seen this vertex, right, we're putting in like all of the possible paths to something, so we might see the vertex multiple times, but we can just ignore it because we know that this path is worse than the path that we already found. And then we just want to print out the distances and a new line, and that should be it. So we need a couple includes. The priority queue is in queue. Yes, we do need pairs, and pairs are in utility. Now, I'm supposed to use the proper 64-bit integer type. Let's see. Do I have to write vector PLL here? I think I might. Yeah, right, because if you look at vector, it takes the type, it takes basically vector of that type, because I guess in theory you might want to use something other than a vector as like the underlying container, and then it takes the comparison function. So we want to change the comparison function, but we're happy to still use vector, so we write it, with these arguments. Okay, so let's see if this actually works. So 5.2, how about that? Cool, so that does work. Yeah, so Dijkstra is actually quite short, right? Like here's the main loop. And if you look at it, it's like literally the same thing as BFS, except that instead of like a deck, we're using a priority queue. And so that means that instead of sort of processing things like level by level, basically based on how many edges they were away, we actually need to process them based on the distance that they are away, and just take the thing with the cheapest distance every time. Of course, this also works for BFS, but in BFS they like happen to get added to the queue in like a sorted order, but that's not necessarily true in this case. So we need to have the queue do the sorting. This gives us an extra log factor, right? BFS is like linear time, and Dijkstra is n log n because this operation, or possibly this operation, takes log n time, or maybe both, probably both. But n log n is almost as good as n. So yeah, pretty pretty simple, but this is definitely an important thing to know. This is like the standard, I don't know, shortest path algorithm. Yeah.